Imagine holding a flashlight on a really dark, perfectly clear night, like
Yeah.
just pitch black out.
Okay, I'm picturing it.
Right, so if you shine it out across a flat field, that beam of light, it travels in a perfectly straight line.
Yeah, absolutely.
But now imagine trying to angle that flashlight so the beam somehow curves around the Earth to, I don't know, illuminate a building in Paris.
Well, you can't do it. Light travels in straight lines. It doesn't bend around corners.
Exactly. It certainly doesn't bend around the curvature of the planet. And for the first half of the 20th century, that exact physical reality, the literal geometry of a sphere, kept humanity trapped. Our communications were essentially blocked by the horizon. Welcome to the Solve Force podcast. From the primal smoke signals of ancient horizons to tomorrow's internet technologies, join us as we decode the invisible networks that connect our world.
Hi, we're Alex and Taylor. For today's deep dive, we are going to look up.
Wow.
Way up. Yeah, we really are. We're exploring the foundational architecture of satellite communications today. So this is basically the story of how humanity bypassed those physical limitations of the Earth's surface. We did it by, literally placing relay stations out into the vacuum of space.
Which sounds simple when you say it like that, but...
Oh, it was a nightmare. I mean,
Right.
It isn't just a story about rockets and hardware, right? The journey to build a global orbital network, it created this massive cascade of engineering problems.
Right, like raw physics problems.
Yeah.
Distance, the speed of light, all of that.
Exactly. And solving those specific problems is actually what forced us to invent the core software protocols that, literally run the modern internet today.
It's so wild to think about, to really grasp the scale of this achievement. I feel like we have to understand the physical prison we were in during the 1940s and 50s.
Well, you're sure. The terrestrial trap.
Yeah, because if you wanted to send a message across the country back then, you were so severely limited by the medium, like you could use shortwave radio, right?
Yeah.
That bounces off the ionosphere.
You could, yeah, but shortwave is notoriously unstable. I mean, it fades, it crackles, it totally relies on atmospheric conditions. It's not great for, commercial use.
Right, so if you wanted to send high bandwidth, reliable signals, like, say, hundreds of telephone calls at once, or a live television broadcast, you had to use microwaves.
And microwaves are exactly like that flashlight beam you mentioned earlier. They operate strictly via line of sight.
Meaning they just shoot straight.
Right. They pierce straight through the atmosphere and head right out into the void of space. They do not bounce off the upper atmosphere, and they absolutely do not bend around the curve of the Earth.
So the horizon itself literally acts as this massive physical wall.
Except...
So to get a microwave signal from, say, New York to Los Angeles, telecom monopolies like AT&T, they couldn't just build one giant tower.
No, the geometry wouldn't allow it.
Right. They had to build this massive continent-spanning chain of concrete and steel towers spaced, roughly 25 to 30 miles apart?
Yeah, roughly 30 miles. Because any further, and the curvature of the Earth physically blocks the beam, you shoot the signal to the first tower, that tower receives it, amplifies it, and then shoots it to the next tower all the way across the entire country.
Which is just a monumental feat of terrestrial infrastructure.
It was. But that model hits a hard stop the exact moment you reach the coastline.
Oh, yeah. You can't exactly pour concrete on the ocean floor for a radio tower.
No, you cannot build a 30-mile-high microwave tower in the middle of the Atlantic Ocean to talk to Europe. It's just not happening. The line-of-sight wall made oceans basically impassable for high-bandwidth wireless communication.
Which left us with, physical cables?
Physical submarine cables, yep.
And laying a cable across the bottom of the Atlantic Ocean is, it's not for the faint of heart.
Not at all. I mean, the first active transatlantic telephone cable, TAT-1, was laid in 1956.
1956, okay.
And this was considered an absolute marvel of its era. It was two massive cables, actually, one for each direction, strung across this jagged, freezing, completely hostile ocean floor.
Just a massive engineering undertaking.
Yeah.
Millions of dollars.
Oh, incredibly expensive. And yet, for all that incredible effort and expense, the capacity of TAT-1 was shockingly, almost comically small.
How small are we talking?
It could carry exactly 36 analog voice channels.
36?
36!
2 entire continents, the United States and Europe, connected by a cable that allowed just 36 simultaneous conversations. That is insane.
Right. If you wanted to call London from New York back then, you didn't just pick up a phone and dial a number.
I'm guessing you had to, like, wait in line.
Basically, you had to
Wow.
book the call in advance, usually through an operator, and it cost an absolute fortune.
Wow.
Transmitting high-speed data or like a live television feed across the ocean. Physically impossible. The bandwidth simply did not exist. The oceans were this massive bottleneck holding back global connectivity.
So how do we get out of this trap? Because obviously we did.
Well, the solution to this bottleneck, it actually didn't come from a telecom executive or a cable company. It came from a British radar officer who also happened to be a science fiction author named Arthur Clarke.
ArthurCClarke. Like 2001, The Space Odyssey, ArthurCClarke.
The very same. In October 1945, which is just months after the end of World War II, Clarke published a paper in a magazine called Wireless World,
Okay.
and the paper was titled Extraterrestrial Relays.
Okay, let's set the stage for 1945 here. World War II has literally just wrapped up. The most advanced rocket technology on the entire planet is the German V2, right?
Yeah, the V2.
Which is essentially a crude, highly dangerous missile that barely brushed the edge of space before just falling right back down.
That's a pretty accurate description, yeah.
And here is Arthur C. Clarke just casually proposing that we built a radio relay station 22,000 miles above the Earth. How on earth did the actual engineering community process a paper that sounded like, well, literal science fiction?
They processed it with a pretty healthy mix of awe and extreme skepticism. Because while the engineering of 1945 absolutely couldn't pull it off, the math in Clarke's paper was totally flawless.
The math actually worked.
It worked perfectly. It relied on fundamental orbital mechanics. You know, when you put an object in orbit, it is essentially falling toward the Earth, but it's moving sideways so fast that the Earth literally curves away beneath it at the exact same rate.
Right, like constantly missing the ground.
Exactly. But the rule is the closer a satellite is to the Earth, the faster it has to travel to avoid just getting pulled down and burning up in the atmosphere.
Like the International Space Station today, right? That's in low Earth orbit, and it, whips around the planet in about 90 minutes?
Yeah, roughly 90 minutes. It's moving incredibly fast. But Clarke calculated what happens if you push a satellite much, much higher.
Okay.
He mathematically proved that if you place an object in orbit over the equator at a very, very specific altitude, approximately 35,786 kilometers.
Or about 22,236 miles, right?
Right. At that exact altitude above sea level, the physics hit this amazing, magical sweet spot.
What happens at that spot? The orbital period matches the rotation of the Earth?
Down to the second. At that exact altitude, the satellite takes exactly one sidereal day, which is 23 hours, 56 minutes, and 4 seconds to complete a single orbit.
Oh, wow.
Yeah. So because it is moving through space at the exact same rotational speed as the planet turning beneath it, it appears to just freeze in the sky.
It just sits there.
Right. To an observer standing in their backyard looking up, the satellite never rises and it never sets. It remains completely, perfectly stationary. We call this geostationary Earth orbit, or GEO.
Okay, so by doing this, you bypass the ocean and the horizon entirely. You essentially build a 22,000-mile-high radio tower, but without the physical tower part.
Exactly. The vacuum of space and the balance of gravity, they do all the heavy lifting for you.
And because that invisible tower is so high up, its vantage point must be massive, right?
Oh, it's huge. Clarke demonstrated that just a single satellite at that altitude can see about 40% of the Earth's surface at once.
40%. So you don't need a chain of towers every 30 miles anymore.
Not at all. You just need 3. 3 of these geostationary satellites spaced roughly 120 degrees apart around the equator, and you can blanket the entire globe in a continuous radio signal.
The whole planet.
Well, missing only the very extreme north and south poles, but basically the whole populated planet.
That is just a stunningly elegant concept. But again, the gulf between this beautiful theory and the grim reality of 1945 was massive.
Yeah, it was a chasm.
Because we didn't have rockets capable of reaching 22,000 miles. We didn't have, solar panels to power a machine in space forever. I mean, we barely had reliable electronics on the ground.
Right, we were still using bulky vacuum tubes for basically everything. But that gap between theory and reality, it was closed surprisingly fast by the geopolitical terror of the Cold War.
The space race.
Exactly. In 1957, the Soviet Union launched Sputnik. And that single little silver sphere just beeping away in low Earth orbit, it triggered an absolute global panic.
It totally kicked off the space age.
It really did. The United States suddenly started pouring incomprehensible amounts of money and brain power into rocketry and, crucially, miniaturized electronics.
Yeah.
So the timeline for Clarke's theoretical math was violently accelerated.
Which really marks this monumental shift in how humanity viewed infrastructure, if you think about it.
How do you mean?
Well, prior to this, if you wanted to dominate global communication, you had to control physical geography, right? You had to own the land to build the towers, or you had to own the massive cable-laying ships to drop copper to the ocean floor.
Right, the terrestrial monopoly.
Exactly. But space offered a completely new paradigm. You could just leapfrog the borders, the oceans, the physical geography entirely.
You could, yeah, but you couldn't just jump straight to 22,000 miles. That was still too far. The rockets of the late 1950s and early 1960s, they were largely just modified intercontinental ballistic missiles.
Right, ICBMs.
Yeah, and they were designed to lob warheads across an ocean, not gently push heavy, delicate communication equipment deep into space.
So they didn't have the lift capacity.
Not even close. Because the lifting capacity was so pathetic back then, the very first attempts to use space for communication had to be radically stripped down.
Okay, which brings us to Project Echo, launched in August 1960. And I have to say, when I first read about Echo 1, I literally thought it was a joke.
It does sound pretty absurd at first.
I mean, it wasn't really a satellite in the way we think of them today at all. It was a balloon.
A giant space balloon.
Literally, a passive reflector. NASA basically packed a 100-foot diameter balloon made of thin mylar, covered it in a highly reflective aluminum film, and just inflated it in low Earth orbit.
Yeah, it was just a giant mirror floating in the sky. It had zero power source. It had no transponders, no amplifiers, no computer chips. It just sat there.
So what was the point?
Well, the idea was that a ground station in the U.S. would just blast a super powerful radio signal straight at the balloon, and the balloon would simply reflect that signal back down to a receiving station in Europe.
But wait, let's go back to our flashlight analogy for a second. If I take a flashlight and shine it at a flat mirror a few feet away, the light bounces back clearly, right?
Right.
But Echo 1 wasn't a flat mirror. It was essentially a massive disco ball hanging 1,000 miles away.
And that shape is the critical flaw. Echo 1 introduced engineers to a really brutal law of physics that governs passive reflectors. When you bounce a radio signal off a spherical object, the geometry of that sphere scatters the signal in all 360 degrees.
Oh, so it doesn't just bounce back down?
No, it radiates out into the infinite depth of the universe.
So the amount of signal that actually happens to bounce at the exact microscopic angle required to hit a receiving dish back on Earth is, what, practically zero?
It mathematically decays at an astonishing rate. With a passive spherical reflector, the signal loss is actually proportional to the fourth power of the distance. Yeah, engineers call this the 1/r to the fourth path loss problem.
Okay, let's unpack that math and make it concrete for the listener. If the distance to the balloon doubles, the signal strength doesn't just get cut in half.
Right.
And it doesn't just drop to a quarter, like standard square laws. It drops to 1/16 of its original strength.
Exactly. Every single mile you add, the signal evaporates exponentially. So to make Project Echo work at all, ground stations had to just scream into the sky with incredibly powerful transmitters.
And on the receiving end?
On the receiving end, the signal coming back down was so infinitesimally weak that normal antennas just heard the background static of the cosmos. Like literally just space noise.
So how do they even hear it?
Well, Bell Labs had to build these massive, highly sensitive horn antennas, and they had to use special receivers called masers.
Masers. Oh,
But
wow.
the crazy part is, to get the masers to be sensitive enough, they had to physically submerge them in liquid helium.
Liquid helium.
Yeah, to cryogenically cool them down to near absolute zero.
Just to stop the heat of the equipment itself from drowning out the signal.
Yep, the thermal noise of the metal itself was louder than the signal bouncing off the balloon.
That is insane. So you have engineers handling liquid helium just to catch a whisper bouncing off a space balloon. I mean, that is an amazing scientific experiment, but it is a terrible business model.
Oh, it's an awful business model.
You can't exactly run a global telecom network if every single receiving station on Earth requires a cryogenic cooling plant.
Exactly. It proved the basic concept that you could use space to bounce a signal, but it completely killed the idea of passive satellites. The industry immediately realized that a satellite couldn't just be a dumb mirror. It had to be a participant.
It had to be an active repeater.
Right.
So an active satellite doesn't just bounce the signal, it actually catches it, cleans it up, and shouts it back.
Exactly. An active satellite has onboard electronic transponders. It receives the faint signal coming from Earth on a specific uplink frequency. Then it uses its own onboard electrical power, which is generated by solar panels, to massively amplify that signal.
Okay.
Then, crucially, it translates the signal to a completely different downlink frequency, so its own loud transmission doesn't interfere with the faint incoming message, and it beams it back to Earth.
And because the satellite is actively focusing and transmitting the energy back down, rather than just passively scattering it off a shiny sphere, the math changes. Right?
Drastically. You move away from that brutal 1/r to the fourth penalty. With an active transmitter, you just follow the standard inverse square law, 1/r².
Which is much, much better.
Oh, massively better. The signal arriving at the ground station is exponentially stronger, which means the ground stations can be vastly smaller, cheaper, and thankfully no longer require liquid helium.
Thank goodness for that. So who did this first?
The military actually took the first shot at this with a satellite called Courier 1B in October 1960.
Oh, early.
Very early. But they had a power problem, so they had to use this weird workaround called store and forward.
Store and forward. How did that work?
The satellite literally had analog magnetic tape recorders inside it.
Like physical cassette tape reels.
Yes, physical spinning tape reels in space. As it flew over a ground station in the US, it would record teletype messages onto the tape. Then, as it continued its orbit and eventually passed over Europe, it would physically rewind the tape and play the messages back down to the ground.
Okay, having moving mechanical parts, literally spinning tape reels in the zero-gravity vacuum of space, seems like a recipe for disaster.
Oh, it absolutely was. Courier 1B only lasted 17 days before the whole thing failed.
Not surprising.
But it was important because it successfully proved that active electronic components could actually survive the violent vibrations of a rocket launch and the extreme radiation of orbit.
Okay, so the military proved it's possible. But the real cultural icon of this era was Telstar 1,
Sure,
right?
definitely.
Launched in July 1962, built by AT&T and Bell Labs. Now, Telstar was a true, real-time active relay. It didn't use tape recorders. It caught the signal and retransmitted it instantly.
Right, instant relay.
And Telstar broadcast the very first live television pictures across the Atlantic Ocean.
Wow.
It was this massive cultural event. They wrote songs about it.
They did. The Tornadoes had a huge hit instrumental track named after it.
Yeah. But there was a massive catch with Telstar. It was not in Arthur-C. Clarke's geostationary orbit.
No, it wasn't. The rockets of 1962 still couldn't reach 22,000 miles with that much weight. So Telstar was placed in a medium Earth orbit, or MEO.
MEO. Okay, what does that mean for the orbit?
Its orbit was highly elliptical. At its highest point, its apogee, it was about 3,500 miles away. But at its perigee, its lowest point, it was a mere 590 miles above the Earth.
That is super low, which means because it was in MEO, it was moving incredibly fast relative to the ground.
Exactly.
I mean, Clarke's GEO satellite takes 24 hours to orbit, so it looks still. Telstar completed an entire orbit in just 2.5 hours.
Which created an absolute mechanical tracking nightmare. Telstar was essentially a speeding bullet crossing the sky.
So you can't just point a dish at it and walk away.
No, to use it, both the transmitting and receiving ground stations had to acquire the satellite as it rose above the horizon, and then physically, mechanically track it as it whipped across the sky before it set over the opposite horizon.
And we're not talking about moving a little rooftop dish like you have for satellite TV.
No, not at all.
The ground station built in Andover, Maine to track Telstar was an absolute monstrosity. It was a giant horn antenna that weighed 340 tons.
It was massive.
And this massive steel structure was so heavy that to move it smoothly enough to actually track a fast-moving satellite, it had to be floated on a thin film of pressurized oil.
Oh, yeah.
And it had to move with millimeter precision.
And all that effort, all that incredible engineering, only bought you a few minutes of connectivity at a time.
Just minutes.
Yeah, because Telstar was moving so fast, the window where it was visible to both the United States and Europe simultaneously, what they call the mutual visibility window, only lasted about 20 to 30 minutes per orbit.
Wow. Imagine trying to run a television network, or worse, a global financial market. With that system, you're transmitting critical data, and then a literal alarm goes off and someone says, sorry, the satellite is setting, we have to wait 2 hours for it to come back around.
Right.
An intermittent connection that requires a 340-ton moving antenna on a frictionless oil bath is not a scalable foundation for global telecommunications.
Not even slightly. It was totally economically unviable. The telecom industry quickly realized that Arthur C. Clarke's 22,000-mile geostationary orbit was not a luxury. It was an absolute commercial necessity.
You had to have it.
You had to. You needed a satellite that appeared perfectly stationary, so ground antennas could just point at one spot in the sky, lock off permanently, and give you 247 coverage.
But they were stuck in this seemingly impossible paradox.
Right, the rocket problem.
Yeah, to be geostationary, you have to be 22,000 miles up.
No.
But getting to 22,000 miles requires a massive rocket or a very, very light satellite.
And here is where the engineering gets incredibly clever. Because if you want a satellite to beam a signal back to Earth, its antenna must remain pointed directly at the Earth, right?
Right.
But in the vacuum of space, things tend to tumble. There's no air resistance. To stop a satellite from tumbling, you traditionally need a 3-axis stabilization system.
Meaning thrusters pointing in all directions.
Exactly. You need gyroscopes, star trackers, and an array of small chemical thrusters to constantly nudge the satellite and keep it perfectly oriented.
But thrusters require fuel.
Lots of fuel.
And fuel is incredibly heavy. And the rockets of the early 1960s simply could not lift a satellite loaded with enough fuel to stabilize itself for years at 22,000 miles. It was a catch-22.
Until we get to Harold Rosen.
Okay, who is Harold Rosen?
He was an absolutely brilliant engineer at Hughes Aircraft Company. Rosen looked at this fuel weight problem and realized he could bypass it entirely by leveraging the fundamental physics of angular momentum.
Okay.
He proposed a lightweight, spin-stabilized satellite.
Oh, this is the spinning top analogy.
Exactly. If you take a toy top and just set it on a table, it falls over immediately. But if you spin it rapidly, it stands perfectly upright, resisting any force that tries to tip it over.
Gyroscopic stability.
Yes. So Rosen designed a satellite shaped like a cylinder. The idea was, once it was ejected from the rocket into orbit, small thrusters would fire once to spin the entire cylindrical body of the satellite up to about 100 revolutions per minute.
Wow. 100 RPM.
Yeah, and this rapid spinning turned the entire spacecraft into a massive gyroscope. It naturally stabilized itself in the vacuum of space, its axis locked rigidly in place, without needing a heavy, complex network of thrusters constantly firing and wasting fuel.
That solves the weight problem beautifully.
Yeah.
You ditch all that heavy station-keeping fuel, the weaker rockets can suddenly carry the payload, and you achieve perfect stabilization.
It was a huge breakthrough.
But wait, I'm seeing a flaw here. If the entire satellite is spinning at 100 RPM, the antenna attached to it is also spinning, right?
Yes, it is.
So the radio beam would just act like a lighthouse sweeping wildly across the universe, only hitting the Earth for a tiny fraction of a second on every rotation. That doesn't work for continuous communication.
And that was the genius of the next phase of the design. The despun antenna.
Despun.
Yeah. The body of the satellite spins at 100 RPM to maintain that gyroscopic stability, but the antenna array is mounted on a motorized bearing right at the top of the cylinder.
Okay.
And that motor spins the antenna in the exact opposite direction at the exact same speed, minus 100 RPM.
Oh, that is so smart. So the body is spinning furiously, but relative to the Earth, the antenna is perfectly motionless, just staring right at us.
Exactly. It was a masterpiece of mechanical engineering, especially considering they had to design bearings that wouldn't literally weld themselves together in the extreme temperatures and the vacuum of space.
Cold welding is a huge problem in space.
Exactly. So the Hughes team built the Syncom series for NASA using this specific design. Syncom 1 failed shortly after launch, unfortunately.
Space is hard.
Very. But Syncom 2 proved the spin stabilization concept actually worked. And then, in August 1964, Syncom 3 was launched.
And Syncom 3 was the holy grail, right? It achieved a perfect equatorial geostationary orbit.
It did. It was parked right over the international dateline in the Pacific, and it immediately proved its worth to the entire world by broadcasting the 1964 Summer Olympics live from Tokyo directly to the United States.
That is incredible. No tracking antennas required.
None.
No 20-minute visibility windows.
Nope. It was a continuous, real-time, a perfectly stationary feed from the other side of the planet.
The success of Syncom 3 must have been the starting gun for the commercial space race.
Oh, absolutely. It changed everything overnight. The United States government passed the Communications Satellite Act, which led to the creation of ComSat, this public-private corporation.
Right.
And then ComSat organized Intelsat, which is this big international consortium, to build a truly global network. And in April 1965, they launched Intelsat I, which was affectionately known as Early Bird.
Early Bird. And this is where the economics of global communication fundamentally broke open, isn't it?
Yes, remember TT1, the massive, phenomenally expensive submarine cable we talked about that could only handle 36 voice channels.
I do.
Well, Early Bird, which was basically just a spinning cylinder weighing less than 100 pounds parked 22,000 miles in the sky, held 240 simultaneous voice circuits.
Wow.
It had nearly 7 times the capacity of the flagship transatlantic submarine cable.
This is just the ultimate lesson in infrastructure disruption. I mean, AT&T and the European post office monopolies held a literal physical stranglehold on transatlantic communication for decades.
Yeah.
If you owned the copper at the bottom of the ocean, you dictated the price of global business.
You held all the cards.
And then literally overnight, Early Bird is turned on, and it single-handedly increases the entire transatlantic voice capacity by a third.
Yep. It bypassed the ocean entirely. The physical moat protecting that submarine cable monopoly was just flown right over.
That's amazing.
And as a result, the cost of international telecommunications just plummeted as space-based competition finally entered the market. By 1969, with the launch of the Intelsat 3rd series, they had a complete ring of satellites covering the globe.
1969, wait. Intelsat the third, is that how they broadcast the moon landing?
Yes, that was the network that beamed the Apollo 11 moon landing live to 600 million people worldwide. Space and infrastructure had officially become the backbone of human connectivity.
Okay, so the geopolitical and economic narrative here is super triumphant. We put spinning cylinders 22,000 miles in the sky, we locked the antennas onto the Earth, and we broke the cable monopolies.
A huge win.
But I want to pause and look at the actual physics of the signal for a minute because, frankly, it sounds totally impossible.
It's definitely mind-bending.
We're talking about beaming a radio wave up 22,000 miles, pushing it through rainstorms and atmospheric interference, having a tiny little satellite catch it, and then beaming it 22,000 miles back down. How does the signal not just completely degrade into pure static over a 44,000-mile round trip?
Well, to answer that, we have to look at the meticulous mathematical accounting that telecom engineers perform. It's known as the link budget.
The link budget.
Yeah, a link budget is essentially a ledger. You add up all the power you are putting into the system on one side, and you subtract all the ways the universe tries to steal that power away on the other side.
Okay, that makes sense.
And the core of this ledger is the Friese transmission equation.
Let's walk through the Friese equation. What are the variables here?
Okay, so it states that the received power at the destination is equal to the transmitter power plus the directional gains provided by the transmitting antenna and the receiving antenna.
Right, because the dish focuses the beam.
Exactly. And then you subtract the free space path loss and any atmospheric attenuation, like your rainstorms.
So simply put, received power equals transmitted power plus antenna gains minus losses. Conceptually simple. But what do those losses actually look like when you are transmitting all the way up to geostationary orbit?
They are almost unimaginably severe. The primary frequency bands used by early satellites, the C-band, operating around 4 to 6 gigahertz, experience staggering free space path loss over 36,000 kilometers.
How staggering.
The loss often exceeds 190 decibels.
Okay, let's translate 190 decibels for a second. Decibels are logarithmic, right? Meaning every 10 decibel drop represents a factor of 10 decrease in power.
That's right.
So 190 decibels of loss means, what does that actually leave us with?
It means the signal arriving at the Earth station is on the order of picowatts.
A picowatt, 10 to the negative 12 watts, a trillionth of a watt.
Yes.
That is an absurdly small amount of energy. To put that in perspective, a picowatt is roughly the equivalent of trying to detect the thermal energy of a single candle burning on the surface of the moon.
That's a great analogy, yeah.
And you're telling me this entire global communications network relied on capturing that candle heat and somehow amplifying it to carry a crystal clear television broadcast?
Yes, it did. The massive antennas catch that trillionth of a watt. But the true hero of this story, the hardware that made it possible to amplify that signal without just drowning it in internal static, is a piece of technology called a traveling wave tube amplifier, or TWTA.
Traveling wave tube amplifier. I mean, it sounds like something straight out of a 1950s sci-fi movie.
It really does.
Why couldn't they just use, modern silicon transistors? We have computer chips. Why use vacuum tubes?
Because in the 1960s, and actually for decades afterward, solid-state transistors simply could not handle high frequencies at high-power outputs.
Oh, they burn out.
Exactly. If you tried to push a microwave signal through an early transistor and amplify it enough to blast it across the country, the transistor would just melt. or it would severely distort the signal.
Which ruins the data.
Right. Engineers needed a way to massively boost the power of a high-frequency wave linearly without corrupting the underlying data. So they turned to vacuum electronics.
Okay, how does a TWTA actually work? Let's break open the vacuum tube.
All right. A TWTA consists of a long, evacuated glass or metal tube. At one end of the tube is an electron gun.
An electron gun, okay?
Yeah. A cathode is heated until it literally boils off electrons, a process called thermionic emission. A very high voltage is then applied, which accelerates these electrons into a tight, incredibly high-speed beam that shoots straight down the center of the vacuum tube.
Okay, I am picturing a high-pressure hose shooting a perfectly straight stream of water. That's our electron beam.
Perfect. Now, wrapped around the outside of this vacuum tube is a wire coil shaped kind of like a long spring. This is called the slow-wave helix.
So we have an electron beam shooting down the center and a metal spring coiled around the outside.
Yeah.
Where does the radio signal come in?
The faint radio frequency signal, the whisper, the picowatt we want to amplify, is fed into that wire helix. Now, radio waves normally travel at the speed of light, right? If we just sent the signal down a straight wire, it would just blow past the electrons instantly. But because the wire is coiled into a spring, the signal actually has to travel round and round the helix to move forward. Oh.
So its forward velocity is drastically reduced.
So the physical geometry of the spring slows the forward progress of the radio wave down until it exactly matches the speed of the electron beam shooting down the middle of the tube.
Precisely. The radio wave in the wire and the electron beam in the vacuum are now traveling side by side at the exact same speed.
Okay.
Let's go back to your water hose analogy. Imagine the electron beam is a fast-moving river.
Got it.
And the radio signal in the helix is a series of water wheels placed right alongside the river.
So the water wheels dip into the river and start spinning.
Exactly. As they travel together, the electric field of the radio waves interacts with the electron beam. The radio wave literally bunches the electrons together and absorbs their kinetic energy. It leaches the raw physical momentum out of the electron beam and converts it directly into pure electromagnetic signal strength.
That is an absolutely brilliant piece of physics. We are boiling electrons in a vacuum, shooting them like a laser, and using them to physically push a radio wave until it's loud enough to cross an ocean. It's incredible, and it amplified signals across extremely wide bandwidths with incredible efficiency and very minimal noise.
Which is exactly what you need.
Right. This analog hardware miracle was the absolute prerequisite for the digital internet. Because to transmit computer data, you need a very high signal-to-noise ratio.
The data has to be clean.
The data must stand out clearly from the background static. If your amplifier is noisy, the bits, the ones and zeros, they'll just flip randomly. A TWTA provided this pristine, immensely powerful signal that early digital protocols desperately needed to function.
Okay, so we've solved the signal strength. We have spinning satellites in GEO. We have de-spun antennas locking onto Earth. We are calculating link budgets in picowatts. And we are using electron rivers to amplify the data.
We've got the physical layer working.
Exactly. The pipe is wide and the signal is crystal clear. You'd think we were ready to just plug the computers in and launch the internet.
You would think that, yeah. But the moment engineers plugged early computer networks into these pristine satellite links, the network completely froze.
Wait, froze.
Throughput dropped to near absolute zero.
But why? If the signal is clear and the bandwidth is high, what broke?
Because while they had successfully engineered their way out of the signal strength problem, they completely forgot to account for an even more rigid law of physics, the speed of light.
Oh, no.
Yeah. They hit the propagation delay problem, or what we now just call latency.
Okay, let's look at the geometry again. The satellite is parked 22,236 miles up. If a computer in New York wants to send a packet of data to a computer in London via satellite, the radio wave has to travel up to space, hit the satellite, and come all the way back down.
Right.
That is a one-way trip of roughly 44,400 miles, or about 71,500 kilometers.
And no matter how good your TWTAs are, nothing in the universe travels faster than the speed of light in a vacuum, which is approximately 300,000 kilometers per second.
Doing the basic math on that, 71,500 kilometers divided by 300,000 kilometers per second equals an unavoidable physical delay of about 238 milliseconds.
Right. And that is just the raw physics of light travel. When you add the atmospheric refraction, the time it takes the ground routers to actually process the data, and the time the satellite's transponders take to shift the frequency, the actual one-way delay from uplink to downlink sits at about 250 to 280 milliseconds.
Which means a full round trip, New York sends a packet, and London sends a confirmation back, takes over half a second. A 500 to 560 millisecond ping.
Exactly.
But wait, let me challenge this for a second. Half a second round trip? That really doesn't sound like a crisis. I mean, I play online video games where my ping occasionally spikes to 500 milliseconds. It's annoying. My character might rubber band across the screen a bit, but the game doesn't crash. Why did this completely break early software?
That's a fair question, but it's because modern software, like your video game, runs on protocols specifically designed to tolerate lag.
Oh, like UDP.
Right, UDP just blasts packets at you whether you receive them or not. It doesn't care. But in the early 1970s, the software connecting mainframes was utterly unforgiving.
Okay, tell me about the early ARPANET. How did it work?
Well, ARPANET was initially built using terrestrial leased telephone lines, just copper wires connecting universities. And on a terrestrial line, the distance is very short and the latency is microscopic, maybe 10 or 20 milliseconds.
Barely noticeable.
Exactly. But because physical errors on analog phone lines were really common, the computer scientists designed a highly rigorous error control protocol called Stop and Wait ARQ. That stands for Automatic Repeat Request.
Walk me through how stop and wait functions.
It is exactly what it sounds like. Computer A transmits exactly one packet of data.
Just one.
Just one. Then it completely stops. It halts all transmission and waits. It will not send the second packet until computer B sends back an acknowledgement, an ACK, confirming that the first packet arrived flawlessly.
Okay, but on a terrestrial copper line, that ACK comes back in 20 milliseconds. The pause is so fast the computers don't even notice. The data just flows like a steady stream.
Right.
But apply that to our 22,000-mile-high satellite.
Exactly. On a satellite link, computer A sends a packet, and then it sits completely idle. It waits 250 milliseconds for the packet to hit London. London checks the packet and sends the ACK. The ACK takes another 250 milliseconds to return.
So for over half a second, the channel is completely dead silent.
Dead silent.
It's like trying to mail a book to a friend, but instead of sending the whole book, you rip out page 1, mail it, and absolutely refuse to mail page 2 until you receive a physical letter back from your friend saying, I read page 1.
Yes.
It doesn't matter if you have a massive fleet of mail trucks, which is your bandwidth, your throughput is entirely bottlenecked by the rigid rules of the communication.
That is a perfect analogy. Because of that half-second silence between every single packet, the overall throughput collapsed. Engineers found they were wasting upwards of 95% of the satellite channel's capacity.
95% wasted.
Yeah. This multi-million-dollar satellite was spending almost all of its time transmitting empty air while the computer stubbornly waited on the speed of light.
So we have a hard collision between software engineering and astrophysics here.
We do.
You cannot code your way out of the speed of light. You can't write a patch that makes a radio waves travel faster than 300,000 kilometers per second. So the hardware basically dictates the architecture. The software has to yield.
Precisely. The computer scientists had to completely abandon the stop-and-wait protocol. They realized they needed a system that divorced the act of transmitting from the act of acknowledging.
Okay.
And this led to the invention of sliding window protocols.
Sliding windows. How does that fix the dead silence?
Well, the two primary algorithms developed were go-back NARQ and selective repeat ARQ. In a sliding window system, the sending computer is allowed to transmit a specific sequence of packets, the window, continuously, without waiting for an immediate acknowledgement.
Oh, I see. It's a conveyor belt.
Explain.
You load box 1 onto the belt, but you don't wait for the person at the other end to receive it. You immediately load box 2, box 3, box 4. You keep the conveyor belt totally packed with boxes.
Yes. The sender keeps blasting packets up to the satellite. And eventually, after that half-second delay, the ACKs for the earliest packets start trickling back down.
Right.
As long as the ACKs keep arriving, the sender simply slides the window forward and keeps transmitting new packets. The channel remains 100% utilized. No dead air.
But what happens if a packet actually gets corrupted by, like, cosmic radiation or it just gets dropped? Does the whole conveyor belt stop?
Under the go-back-N method, if packet number 5 is corrupted, the receiver rejects it. The sender eventually realizes packet 5 was lost, and it has to literally go back end spaces, and retransmit packet 5 and every single packet it's sent after 5.
Wow, that sounds really inefficient if the latency is high. You'd be resending a ton of good data just because one single packet dropped half a second ago.
It is very inefficient, which is exactly why selective repeat ARQ became the standard.
How is that different?
In selective repeat, if packet 5 is lost, the receiver buffers packets 6, 7, and 8, and specifically asks for just packet 5 to be retransmitted. The sender slips packet 5 back onto the conveyor belt without disrupting the overall flow.
This is totally foundational. The latency crisis imposed by geostationary orbits directly forced the creation of these sliding window mechanisms.
It did.
And these exact mechanisms were literally baked into TCP, the Transmission Control Protocol,
Yeah.
which still manages almost all reliable internet traffic today.
They are.
Your laptop is using satellite-era logic to stream this very audio. It's
Yeah,
crazy.
it's a beautiful legacy. But solving latency was actually only half the software battle.
Oh.
Yeah, they had maximized throughput for two computers talking directly to each other, but satellite transponders are incredibly expensive. You cannot afford to dedicate an entire satellite channel to just a single pair of computers.
That makes sense.
You need dozens, maybe hundreds of ground stations, all sharing the same satellite frequency.
Right, and if they are all sharing the exact same radio frequency, how do you stop them from constantly talking over each other? I mean, if two ground stations transmit at the same time, the radio waves collide at the satellite, the data scrambles, and the packets are destroyed. How do you orchestrate traffic without a central conductor?
The answer to that question actually began far from the space race, on the beaches of Hawaii, with a visionary computer scientist named Norman Abramson and a project called AlohaNet.
Let's dive into AlohaNet. What was the exact problem Abramson was trying to solve in Hawaii?
So, in the late 1960s, the University of Hawaii had computer terminals scattered across different islands, Oahu, Maui, Hawaii, and they needed to connect all these remote terminals to a central mainframe located in Honolulu.
But laying dedicated underwater telephone cables between all the islands was prohibitively expensive and prone to breaking.
Exactly. The ocean floor there is really rough.
So he decides to use wireless radio instead.
Right. But radio is a shared medium. If Maui and Oahu both transmit a data packet on the exact same frequency at the exact same millisecond, you get a collision.
So what's the standard solution?
Well, the traditional rigid telecommunications approach would be to install a master controller that assigns specific rigid time slots to every island. Maui, you can only talk during millisecond 1. Oahu, you talk during millisecond 2. This is called time division multiple access.
That sounds orderly. Why didn't he just do that?
Because computer data isn't a continuous phone call, it's highly bursty.
It's bursty.
Yeah, a terminal might sit idle for 20 minutes while a user types out a command and then suddenly blast a massive chunk of data all at once. If you use rigid time slots, the network spends most of its time cycling through empty slots waiting for data that isn't there. It's wildly inefficient.
I see.
Abramson wanted a system that could handle unpredictable, bursty traffic perfectly, so he invented random access.
How random? Did they, listen to see if the channel was clear before transmitting?
In pure Aloha, they didn't even listen.
Really?
It was absolute anarchy. If a terminal on Maui had a packet, it just broadcasted it instantly. If the central mainframe in Honolulu received the packet clearly, it beamed back an ACK.
And if Maui didn't get an ACK, it just assumed its packet collided with another island's packet.
Exactly. But here is the true genius of AlohaNet.
Yeah.
Back-off algorithm.
Okay, how did that work?
If Maui and Oahu collide and they both immediately try to resend their packets as fast as possible, they will just collide again forever.
A total gridlock.
Right. To break the loop, Abramson programmed the terminals so that after a collision, each terminal would wait a randomly generated amount of time before trying again.
Okay, so Maui rolls the dice and waits, say, 12 milliseconds. Oahu rolls the dice and waits 47 milliseconds. The second time around, they don't overlap. The collision resolves itself purely through randomized mathematics.
It was incredibly elegant. AlohaNet proved that distributed random access packet switching worked perfectly over radio waves. So in the mid-1970s, DARPA, the military research agency building the early internet, decided to apply this Hawaiian logic to space.
They created SatNet.
Yes, the Atlantic Packet Satellite Network. It linked the U.S. and Europe via an Intelsat Vibe geostationary satellite.
So they basically took Aloha to orbit. Did it work?
It crashed spectacularly.
Why? If random backoff solved collisions in Hawaii, why didn't it work over the Atlantic Ocean?
Because of our old nemesis, The speed of light.
Ah, the latency again.
Yes. In Hawaii, the islands are close together. The latency is practically zero. If you collide, you know instantly and you back off instantly. But on SatNet, the satellite is 22,000 miles up. The one-way delay is 250 milliseconds.
Ah. So if a ground station in West Virginia and a ground station in London both transmit at the same time, neither of them will know they collided until half a second later.
Exactly. By the time West Virginia realizes its first packet was destroyed in a collision, it has already enthusiastically transmitted 20 more packets right behind it, all of which are now just piling up in the chaos.
What a mess.
The 500 millisecond feedback loop made pure Aloha completely unstable under heavy traffic. The network just dissolved into continuous collisions.
So how do you manage shared access when everyone is essentially blind to what happened half a second ago?
You need a hybrid approach. Engineers Vint Cerf and Bob Kahn, along with teams at Bolt Beranek and Newman, or BBN, they developed a highly sophisticated channel access algorithm specifically for SatNet called PODA.
PODO, Priority-Oriented Demand Assignment. How does PODA bridge the gap between rigid time slots and chaotic random access?
PODA essentially split the difference. It conceptually divided the satellite channel's bandwidth into frames, and each frame had two distinct sections: a contention subframe and a reservation subframe.
Okay, explain contention first.
The contention subframe operated very much like Aloha. It was a free-for-all. Any ground station could use this small slice of time to fire off very short, bursty pieces of data, or, crucially, to fire off a tiny reservation request packet.
Why didn't they collide constantly?
Because the packets were so small, the risk of a catastrophic collision was much lower.
So I use the chaotic contention slot to just quickly shout, hey, I have a massive file to send.
Right. And that request goes up to the satellite and is broadcast down to every single ground station on the network. Every station maintains the exact same synchronized, distributed ledger of who has requested time.
Oh, that's clever.
So when your request is officially logged, the algorithm automatically grants you dedicated, safe space in the reservation subframe.
So the reservation subframe is the orderly part. Once my slot is booked, I can stream my massive file without any fear of anyone talking over it.
Exactly.
It is like a crowded town hall meeting. The contention slot is people randomly shouting out, I have a question. And the reservation slot is the moderator saying, okay, the microphone is yours for the next 5 minutes, nobody interrupt.
That is an excellent way to conceptualize it. PODA turned the satellite from a simple dumb mirror into a highly dynamic, intelligent switchboard.
It managed the traffic.
It proved that you could optimize a phenomenally expensive satellite transponder, seamlessly mixing the chaotic bursts of computer keystrokes with the heavy, continuous streams of voice or file transfers without wasting a single millisecond of bandwidth on empty silence.
And all these foundational pieces, the spin-stabilized geostationary orbit, the TWTAs capturing picowatts, the sliding window protocols handling the half-second delay, and PODA managing the traffic, it all culminated on a very specific date. November 2010, 1977.
The three-network demonstration.
Yeah.
This is arguably the moment the modern internet was truly born. Up until this point, networks were mostly homogeneous.
Meaning, ARPANET computers talk to ARPANET computers. SatNet talk to SatNet.
Right. DARPA wanted to prove that their new software protocols, TCP and IP, the Transmission Control Protocol, and the Internet Protocol, could act as a universal translator across totally hostile, incompatible physical mediums.
The physical route of the data in this demo is just staggering.
Walk us through it.
Picture this. The data begins its journey in a large, moving panel van, driving down the Bayshore Freeway in the San Francisco Bay Area.
Literally driving on the highway.
Inside the van is a computer transmitting data over a localized packet radio network, PRNet. Those radio packets are picked up by a gateway device in California. The gateway strips off the PRNet radio envelope, wraps the data in ARPANET formatting, and pushes it onto terrestrial copper phone lines, sending it 3,000 miles across the United States.
Right.
The data arrives at another gateway on the East Coast in West Virginia. This gateway reformats the data again, wraps it for SatNet, and blasts it out of a massive parabolic dish up to an Intelsat Think satellite parked 22,000 miles above the Atlantic.
And then the satellite catches it.
The satellite catches the signal, translates it, and beams it down to a ground station in Europe, specifically at University College London or the station in Tannum, Sweden. The data hits Europe, turns right around, bounces back up to the satellite, comes back down to West Virginia, re-enters the ARPANET copper lines, and travels back across the U.S. to finally terminate at a computer at the University of Southern California.
A total round-trip journey of 94,000 miles.
94,000 miles. It crossed moving vehicles, localized radio waves, buried copper lines, and the vacuum of space. And the sheer mechanical friction of this is what really blows my mind. These networks were profoundly incompatible.
Completely different physical layers.
Yeah, ARPANET was fast with low latency. SATNET had a massive half-second delay. PRNet had crazy high error rates because the van was literally driving under bridges and losing the radio signal.
And yet, it worked flawlessly. TCP and IP insulated the actual message from the chaos of the physical layers. The Internet Protocol just chopped the data from the moving van into fragments, routed them through the labyrinth of gateways, tolerated the massive 500 millisecond satellite delay, caught the errors caused by the highway bridges, retransmitted the missing pieces, and reassembled the pristine message at USC without a single bit being lost or corrupted.
It's just magic. This demonstration represents a profound philosophical shift in communications, too. For decades, the dominant paradigm in wireless communication was the broadcast model. Think of a giant AM radio tower.
The one-to-many topology.
Exactly, 1 to N. A single, massively powerful, centralized transmitter broadcasting a message to millions of completely passive receivers in their cars or living rooms.
And in that paradigm, control is highly centralized. Whoever has the capital to build the massive tower and hold the broadcast license basically controls the entire narrative. The receiver has no voice.
But the architecture of SATNet, the innovations of Aloha and Poeni, they violently smashed that paradigm. By treating the satellite as a shared, contention-based packet switch, they totally transformed a broadcast medium into an interactive network.
It shifted from one-to-many to many-to-many, M to M. Every single node, every ground station, and eventually every personal computer became both a listener and a talker.
It's so democratizing.
It really is. Packet switch satellites decentralize power. They proved that the network itself could just be a dumb pipe, whether that pipe was a copper cable or a 22,000-mile microwave beam, while the smart intelligence was pushed to the extreme edges, to the users.
The passive audience was erased. The broadcast medium was pacified and integrated into a democratic grid.
The receiver literally became a participant.
So let's step back and look at the massive journey we've taken today. We started on the ground, trapped by the physical walls of line-of-sight microwaves and the meager 36-channel capacity of those early undersea cables.
We did.
We explored ArthurCClarke's visionary orbital mechanics, and then watched Harold Rosen spin-stabilize a cylinder to finally conquer the geostationary void without running out of fuel.
We dove into the rigorous math of the link budget, conceptualizing how engineers captured picowatts of energy and amplified them using the electron rivers of traveling wave tube amplifiers.
And then we confronted the speed of light. We saw how a 250 millisecond delay completely broke 1970s software, forcing the absolute abandonment of stop-and-wait IRQ in favor of continuous sliding window protocols.
Right, which we still use.
We explored how Norman Abramson's randomized AlloNet evolved into the sophisticated PODA scheduling algorithm to manage orbital traffic. All of it culminating in the 94,000-mile triumph of the 1977 demonstration that proved the Internet could wrap around the planet.
The application of this history is just incredibly relevant to our daily lives. I mean, the next time you experience a slight half-second lag on a global video call, or the next time you stream a live event from across the planet, realize the sheer magnitude of what is happening under the hood of your device.
It's easy to take for granted.
It is. But you are interacting with software protocols that were specifically written to negotiate with the immutable speed of light and the unforgiving vacuum of space. The sliding window algorithms in your laptop right now are direct, unchanged descendants of the code written to handle a geostationary satellite delay.
It's amazing. But I want to leave everyone with a final, highly ironic thought to mull over.
What's that?
We spent this entire deep dive talking about the Herculean effort to get out of low Earth orbit. We talked about how Telstar, buzzing around at a few thousand miles up, was an absolute tracking nightmare.
Oh, yeah. The 340-ton horn antennas.
The 20-minute windows, it was intermittent and chaotic. We desperately needed the stationary 24/7 simplicity at GEO coverage. That was the holy grail. But look at what is happening today with mega constellations like SpaceX's Starlink. We are seeing a massive shift back to LEO.
It is a perfect cybernetic loop of engineering history. In the 1960s, we solved the tracking problem by moving to GEO. But by solving the tracking problem, we instantly hit the latency problem, the half-second speed of light delay.
And we couldn't fix the physics, so we wrote software to tolerate the delay. But today, the demands of the modern internet, like high-speed gaming or algorithmic financial trading, they can't tolerate that half-second delay anymore.
So, armed with cheap, reusable rockets and vastly superior computer software that can handle rapid, seamless handoffs between hundreds of moving targets in the sky, we are returning to low Earth orbit.
It's full circle.
We are going back to the chaotic, fast-moving swarms to escape the very latency penalty of GEO that we just spent this entire deep dive dissecting. We solved a mechanical problem to face a physics problem, and now we are using computational power to solve the physics problem by returning to the mechanical challenge. It is just a continuous, breathtaking evolution of human ingenuity pushing against the boundaries of the universe.
That is perfectly said. Next time you step outside on a clear night, look up. You aren't just looking at stars. You are looking at the invisible orbital backbone of the human race, the ultimate architecture of our connected world. Thank you for joining us on this deep dive.